The Unified Chemistry exam paper for A-level chemistry on the OCR specification is an absolute beast. You can be tested on absolutely anything from the A-level, and it's only an hour and a half, and it's only 70 marks with no multiple choice whatsoever. It's a really tricky paper, and the scenarios that you're often presented with are a lot of heavy application. What I want to do, though, is take you through this example, which is the 2018 paper, and show you where all the links are to the specification content and give you full guidance with my answers to the questions based, of course, on the official mark scheme. There's also some specific content covered in this paper that I've already got lots of tutorial videos for, and you can check out all the links to that in the video description. I'll come back as often as I can remember to make sure that those links are kept updated for you. Let's start off then with question 1. I'm going to try and stick to blue pen all the way through this, but I'm already conscious that I've failed on that achievement before I've got started because I know that later on with the mechanisms they're in black, but that's not the point. With question 1, this question refers to the elements in the first 3 periods of the periodic table. So we are capping ourselves here on just hydrogen through to argon. Don't get carried away and start looking at the other sections. I think this question is really important when it comes to the instruction of reading the question for information. Select an element from the first 3 periods that fits each of the following descriptions. First off, the element that forms a 1- ion with the same electron configuration as helium. So if it's a 1- ion, that means the atom has picked up an extra electron, which means it can only really be hydrogen anyway, but just to match up to that, the electron configuration there is going to be 1s2 anyway, so the first one is hydrogen. The element with the highest first ionization energy. Right, well here you need to know the trend from module 3, which is for ionization energy. The top of the group and to the right-hand side is where your highest ionization energies are going to be. And that's because you've got that small atomic radius, you've got that same constant level of shielding as you move across the period, but you've got the nuclear charges increasing, all of that good stuff. And so here it's going to be helium because it's positioned right in that top right-hand corner. I think a lot of people here automatically go to fluorine because you learn so much about fluorine being the most electronegative element, but I want you to focus on the correct trend here. Next up, the element in period 3. Now this is quite specific because we're ruling out there quite a lot of elements with this, which has the successive ionization energies shown below. So here what we're looking for is the big jump. This is very, very much like a question you would expect on paper 1. And the big jump here is between the second and third ionization energies. That tells me that there were 2 outer electrons on the element. So that means it was in group 2, period 3, it's magnesium. Next up, the element which forms a compound with fluorine that has octahedral molecules. Now here we're looking at group 6. Because to form an octahedral molecule, you're going to need to form 6 covalent bonds around the central atom. And so that central atom has got to be in group 6 here, really, for this. Yeah, there are other options for this, but we know that we're looking at individual elements here in that first section. So just from hydrogen through to argon on the periodic table. I'm also going to make the estimation here that this is going to be from period 3 because we're looking for that hypervalency. We're looking for the idea of having more than just the octet rule for our outer shell. So here our correct answer to 4 is sulfur. An element which reacts with water to form an acidic solution. We're rocking into module 3 with this one, looking at the halogens topic because you need to be aware of this example of a disproportionation reaction. There it is, Cl2 with H2O giving you HClO and HCl, the HCl here being that acidic aspect of the solution. So our answer here is chlorine, but they did accept fluorine as well. The element X, which forms a compound with hydrogen with a molar mass of 34 grams per mole. This one's not too bad, I don't think. All you need to do for this is consider that if you've got 3 hydrogens in there, that's going to be -3 from the 34. That leaves you with 31, meaning that X has got to be phosphorus. So that's quite straightforward, actually. Next up, an element which forms a compound with hydrogen, in which the element has an oxidation number of -4. This one's quite tricky. Since hydrogen is very commonly +1, I know we talked about it being H-1 further up the same question, but since it's very commonly +1, this suggests the compound formula is XH4. 4, because to counteract the 4H pluses, your element would need to be -4. And so I'm going to estimate here that the formula is XH4. And straight away, that makes me think of the group 4 elements, and it makes me think straight away of carbon, because that would be like methane. And so that'd be CH4 in this case. So the correct answer here is carbon. For this final one, a lot of students ask me about this and say, are we meant to know the density calculation? Are we meant to be aware of the calculation for density here? So density times volume gives you mass. Well, no, not necessarily for this one. You've got a lot of clues in this question where you could have a bit of a muddle through it and actually get to the correct answer. The biggest clue is what I've highlighted on the right-hand side. The clue here is that we're told about room temperature and pressure. So there's a couple of things tied to this. First off, when I see room temperature and pressure in a chemistry exam, that straight away makes me think of the condition attached to the molar gas volume of 24,000 centimeters cubed per mole, or 24 decimeters cubed per mole, if you will, depending on the units, of course. And so straight away, that made me think of that. The other thing that I was thinking about was some elements from the periodic table at room temperature and pressure form molecular structures. So, for example, nitrogen is N2, or chlorine is Cl2 at room temperature and pressure. And so I started thinking about a whole molecule rather than just an individual element from the periodic table. Now, you've also got here the density value given to you by the question of 1.33 times 10 to the power of -3. Or if you are just trying to make sure that you can do this nice and quickly, we've got 0.00133, and that's grams per centimetre cubed. That per centimetre cubed aspect there is also what stuck out to me, along with the idea that we use a lot in organic chemistry, that in order to identify an element, we very often use molar mass. We often use molar mass to identify an organic compound when we look at things like mass spectrum. So the idea here of trying to get to maybe mass in grams, or better yet, grams per mole, really stuck out to me. So playing with this number, what you can do is, if you have the density and you multiply by the molar gas volume, you actually get molar mass units out here. And if you run through these numbers like I've done at the bottom here, we've got our density multiplied by the molar gas volume. That gives you a grams per mole answer here of 31.92, which could read as 32 grams per mole, and identify our element at room temperature and pressure as oxygen, because it would exist as O2. Next up, we've got this question, which they did get critiqued a little bit for online, and I'll explain why for this. But we've got some properties of period 3 chlorides. And so we've got here sodium chloride, magnesium chloride, silicon chloride, phosphorus chloride, and sulfur chloride. All different types of formula in here, but really what we're looking at is a divide here down the middle. And so the 1 and 2 group, period 3 chloride, so that's the sodium chloride and the magnesium chloride, have got very different properties from the others over here, from groups 4, 5, and 6, which are silicon chloride, phosphorus chloride, and sulfur chloride. And what we need to do is explain the properties shown in the table in terms of bonding and structure. So what we're explaining here is the electrical conductivity difference and the melting point difference. Now, in explaining the electrical conductivity difference, I want to focus on the only difference here, which is that we've got good electrical conductivity when it comes to the giant ionic lattice structures in there. Poor is seen throughout all the rest of the others, so I'm going to focus on this being a difference just here. When it comes to the melting point, well, we can angle our answer in either direction, really. But because we've got a distinctive difference here between high and low, it's quite clear cut for this. There's no difference in solid and liquid, as you can see, like we've got here for the electrical conductivity. With melting point, we've just got this clear-cut difference of high versus low with the giant ionic lattice structures versus the simple molecular lattice structures on the right-hand side. So let's have a look at the answer. So first off, with my first bullet point, and this is matching the mark scheme for this, I would mention that MgCl2 and NaCl are both giant ionic lattice structures. I want to make sure that I point out what kind of bonding and structure I have straight away. And when molten, the ions here are mobile, which makes them good conductors of electricity. Please don't write something you'll have picked up from GCSE. Please don't write that they carry the charge. A lot of people say that when molten, the ions are free to move and can carry the charge. This carry the charge thing doesn't mean anything. We need to put in that the ions are mobile, when molten. We don't need to mention aqueous here because that's not a factor in this question at all, but we need to mention that for the giant ionic lattice structures, that when molten, the ions are mobile. Then moving down, I'm going to talk about the simple molecular lattice structures. They're all simple molecular lattice structures. First off, that's something I definitely want to mention here. And then the simple molecular lattice structures have all got molecules which are held together by London forces. Now, being quite specific here, I'm not just saying intermolecular forces. I have seen that accepted in a lot of other questions in different years, but whenever you can talk about intermolecular forces, do try and be specific. Now here, because you've got different elements within each structure, your automatic assumption here could be that here you've got permanent dipole-dipole, but for example, the SiCl4 would be non-polar, so it would actually only have London forces. And for the other two, even though looking at them, you would assume it would be permanent dipole-dipole, the mark scheme didn't allow it. This is where they got critiqued a little bit, because how are you meant to know that they've got such similar electronegativities that they're only going to have London forces? So they did get a little critiqued for that online. And the feedback from that is that they'd be a bit more specific in future questions. So here, what we then point out is why there's a difference in the high and low melting points, and we say that the London forces in the simple molecular lattice structures are weaker than the ionic bonds in the giant ionic lattice structures, which explains why the giant ionic lattice structures have got a higher melting point. And the reverse argument for this final bullet point is obviously okay. Moving over to question 2. This question has got a bit of application when it comes to some cobalt-2 work in transition elements. It links up to the copper-2 and I suppose most of the other transition element complex ion work as well. But it kicks off with a bit of graph work. Now, I suppose this is students' big fear, that there's going to be a complicated graph in the exam. But they were quite generous with the mark scheme of this. The only thing that I noticed was it was a little tricky to get their exact gradient boundary when you have to do the tangent to the curve. And I thought the curve was a little tricky to do. So for this question to begin with, I'm going to zoom out a little bit for this one. We're told that we've got 50 centimeters cubed of H2O2 in a conical flask. The student adds a small spatula of MnO2 and quickly connects the flask to a gas syringe. And the volume that we're collecting here is, according to the reaction equation, oxygen gas. So here we go. Now, you'll notice we actually have a reading here. At time 0, here's 0 centimeters cubed of oxygen. That means that we do actually need to make sure that our line goes, our line of best fit, goes right down to the origin, and I'll demonstrate that on my graph on the next page. Notice the instructions. Try to ignore my gradient calculation here just for a moment, but notice the instructions. We're told to process the results as outlined below. We need to plot the graph, and then we need to use the graph to find the rate of reaction at time equals 500 seconds, and we need to show your working on the graph and in the space below. So let's have a look at my graph. Try not to get overwhelmed because I know it's really good. So I've got the graph just here. Also, just a reminder, I'm using lots of different colours throughout this tutorial for my penmanship. Please make sure you don't use anything other than a pencil or a black pen in your exam. All right? And don't highlight your answers, okay? So, what I've got here are all my plotted points, and I can't tell you how long that took. So, all the plotted points are on here, making sure, as I mentioned before, that we've got this point down here at the origin, that 0, 0 point. Don't use a crazy scale that goes up in 3s or anything like that. Make it nice and clear. You can see here that using the large squares, I've gone up in 5s, going up the y-axis, and then I've gone up in 200s across the x-axis. I think what you also might notice about this, if you're not really confident with the graphs in the exam, is that I've gone right to the edge of the little plotted section. Don't be afraid to use the edges as your axes, because you might find actually that's the best way to get a straightforward scale. And there we go. So I've got all my plotted points. I've got my line of best fit. What I've done here as well in the blue, and again, don't use a different colour in the exam. But in the blue then, I've got my tangent. Now, I was told by the exam question to find the rate of reaction at 500 seconds. So what I've done is I've gone to 500 seconds on the x-axis, and I've gone right the way up here to my line. There we are. And I've got my tangent to that point on my curve, which is my line of best fit. And what I'm going to use here with you is this little image of a ruler to demonstrate how I would achieve that tangent in the exam. Now, the middle of my ruler has got this little sort of size controller thing on it, so I'm going to go a little bit off for this. But what you need to do is, I'm working towards a sunset. And my sunset has got to be for this bit just here. So let's have that again. So just here, this is where I want my sun to set. And the reason for that is that's the point at which my line for 500 seconds going up here meets my line of best fit. So this is my sun just here, and I want it to set behind the line. And the line is my ruler. So I want the curve to go towards this point, and I want the sun to set behind the line. So if I have a little point just here, here's my sun. I want to move the ruler towards the sun to allow it to set behind the line of the ruler. So I move it towards it like that. And so that point, there it is, it's gone. It was here. There it is, you can see because the ruler now drops behind the lines. That's where it was. It's set behind the ruler line. It's set on the horizon. And I've done that because then what I do is, by moving the ruler towards that point just there, I make sure that there's an equal distance all the way under the curve, right until that point. So the last bit to dip behind the line just here is going to be this point. And it works every time. And so it sets behind the line like that. I've got my big blue diagonal line on there for my line of best fit. And when I shift my ruler out the way, you can see I've got my tangent. Now look at what I've done with my tangent. I've gone right through the edges here for this. So I've gone right the way up here and right the way through here. And so my triangle to find the gradient is all of this bit here. Now I've done that for a number of reasons. First off, when I start labeling up the numbers then down here, it's really obvious to the examiner because I'm not doing too much writing on the graph paper like I've done here. I'm doing all this bit up here and down here as well. It's really obvious where I've crossed through for them, so it's easier for them to mark. And that's part of the battle with this. The other thing is, a lot of the examiner comment summaries say that you need to draw bigger triangles when it comes to this tangent to a line of best fit. So I'm following the feedback there from the examiner. Now when I do this calculation, I've done it on the graph just here, but I'm just going to hop back to the previous page because I've also done it down here. I've got my gradient then at t equals 500 seconds from my tangent, and there's my calculation, change in the y-axis divided by the change in the x-axis, and that gives me a rate of reaction of 0.0403, which I'm going to quote here just to two significant figures, just because the mark scheme went to that. But on the day of the exam, I mean, I'd probably still quote it to 3 sig fig. But the mark scheme was looking for anything that fit inside the region to 2 sig fig of 0.037 and 0.047. I think personally this is a little bit high at this end of the scale, but mine fits inside this boundary, so it's all good. This is a really good question for practicing because you could do this question 3 or 4 times and you might not get the exact same graph every single time or the exact same line of best fit. I would really practice with this one. Examine the mark scheme, look at the kind of thing they're looking for. So for instance, they wanted you to make sure that you went right through the origin down here with your line of best fit. They were looking for you drawing the tangent in the correct location, matching up to the 500. There's loads of stuff you can pick from this, but here's my model answer for you, drawn out and explained so you can see exactly what I've done for this. Okay? Right, next part. Here we go. The student allows the reaction in equation 2.1 to proceed until no more gas is evolved. The volume of oxygen in the syringe is now 55 centimeters cubed, measured at room temperature and pressure. Calculate the initial concentration of the hydrogen peroxide, the H2O2. Give your answer to 2 sig figs. We've got a nice precision requirement just there. Always check for those. If you give a numerical answer in the exam, check for a precision requirement. And if not, just go with the precision requirements of the data you're already using. Now, over here, I've done a little snippet of the equation from a previous page, because the other thing about the unified chemistry exam that I've noticed is that later parts of the question on much later pages relate to an earlier part of the question, which you might have seen 2 pages ago. So make sure that you remember that you are still in the same question, even if you're 3 pages ahead, because there aren't many questions in a unified paper compared to the others, because there's no multi-choice. And so it's very easy to think you've actually moved into a completely different question and that the information from 3 pages ago isn't relevant anymore. All the more reason as well when you have a graph, because a graph takes up a full page. So here, what I've done, I've calculated the number of moles of oxygen. That's what I'm doing here. So that's going to be 55, which is my volume just there. So this is going to be moles. Moles equals concentration, moles equals volume over molar gas volume for this. Nearly gave the wrong calculation to you. And the reason I'm using this calculation is because I've been told that I'm at room temperature and pressure. So my number of moles here is going to be 55 centimeters cubed divided by 24,000. You could convert the 55 centimeters cubed into decimeters cubed and use 24. So that would be decimeters cubed per mole for that molar gas volume. But I just quite like saving a step. And so my number of moles of oxygen here is 2.29 times 10 to the power of negative 3 mole. Now the ratio, which is why I've got this little snippet just here, of oxygen back to the hydrogen peroxide is 1 to 2. And so in order to find out the number of moles of hydrogen peroxide that would release this much oxygen, I need to double that mole value. So my mole value for the hydrogen peroxide is 4.58 times 10 to the power of negative 3. Concentration of the hydrogen peroxide then, that is going to be moles over volume. So I got it right this time. The volume here, I think this is really sly. So I'm actually going to go back quite a bit. As I mentioned here, you're told the volume of the hydrogen peroxide on page 4, and then you need to use it on page 6. Personally, I think that's really unfair because it can leave you in a bit of a panic, but it's all part of the unified fun in the unified exam. So moles over volume here gives you a concentration value for the hydrogen peroxide of 0.092. There we go. Hydrogen peroxide can act as an oxidizing agent or as a reducing agent. Some standard electrode potentials are shown below. So we've got an electrochemical series here, but I think they did quite a sly tactic. Check out these standard electrode potentials down here. They're not in the right order. And the reason for that is because they've separated, they've even put a little gap through the middle, the hydrogen peroxide containing half equations in a different section. Now here you're asked to demonstrate by the question hydrogen peroxide acting as a reducing agent. Now, when you're given an electrochemical series in the exam, the conventional way, the way they're meant to do to write these, is for all of the electrons in each half equation to be on the left-hand side, meaning that although they are, of course, equilibrium, there they are, they're all written at the moment in the reduction direction. So that's the conventional way of doing this. Now, what you can then use about that to your advantage is that on the right-hand side here, these are all reducing agents, and these are all oxidizing agents when they are all written this way. So straight away, you'll notice I've put a big line here through the second one because I know that the hydrogen peroxide on the right-hand side over here is the reducing agent one I'm after. So I've got rid of this one because it's not useful to me. Now, to demonstrate this hydrogen peroxide redox system behaving as containing a reducing agent, I need this particular redox system here, this half equation, to shift left when it's combined with another redox system from down here. And the way that I'm going to get that is by making sure that the standard electrode potential of this top redox system, this top half equation here, is less positive than the one I want to combine it with. And so the only one out of the two down here that I can select as my partner for this top redox system is going to be the manganese containing one just here. So I'm going to combine the very top with the very bottom, hence the two little ticks just here. What I've done before I do my combination is a little update. You can see I've written my updates here. I have now written the top equation in the other direction because now I want that to demonstrate oxidation. So I've got my electrons as a product just here so that I can effectively combine it with the other one, which needs to be a reduction as it's written here. But you'll notice I've got a few extra electrons now than I did before. And the reason for that is I want the electrons to cancel out when I do this combination. So I've had to do a multiple of each equation. And so I've done the top equation times 5 and the bottom equation by times 2. I then combine to give one big ridiculous equation just here and cancel down. As you can see, I've gone through and I've cancelled down anything that appears the same on both sides, leaving me with this overall equation at the very end. Check the mark scheme for the split up of the marks, but really you want to focus on how to get the correct answer. At this point, if you're looking at getting really ready for your exam, you want to focus on the correct chemistry, the correct answer, rather than trying to think, what would I have got 1 or 2 marks for here? Moving on to the next part, and this is what I was mentioning before at the start of question 2. Talking about the application of the transition elements work. Cobalt really isn't on the specification for OCR-A, it used to be, but it isn't really here anymore. And this whole section is a little bit of application when it comes to what's happening with these cobalt-2 complex ions based on what you do in the A level to do with chromium, to do with copper, to do with manganese. So it's not too alien. Particularly here, we're focusing on copper. Cobalt-2 forms complex ions with water ligands and with chloride ligands. With water ligands, cobalt-2 forms a pink octahedral complex ion, and you've got the formula for that. And with chloride ligands, cobalt-2 forms a blue tetrahedral complex ion. The student dissolves cobalt 2 sulfate in water in a boiling tube and a pink solution forms. So the pink solution is going to contain that. In the first experiment, in a water bath at 100 degrees C, concentrated hydrochloric acid is added dropwise, and the colour of the solution changes from pink to blue. So by adding the hydrochloric acid, we've introduced the Cl- ligands. So they are now available in the solution. And what happens is they undergo a ligand substitution with the H2Os that are present in the complex ion. And what we form is this complex ion shown in the equation, which is demanded as part of section 1 of our answer. So the accessibility of these Cl- was produced by the HCl being added, and they reacted and did this ligand substitution with the pink complex to form this blue complex here in hot water in the 100 degrees C water bath. That gives us this reaction equation, which is exactly the same as the copper 2 one that you will have learned as part of your A-level, except it's got cobalt in. Just be careful that you don't accidentally write copper. Then, in experiment 2, they put the boiling tube in an ice water bath at 0 degrees C. The colour of the solution changes from blue to pink. So even though the Cl- ligands are available, the equilibrium shifts to the left and makes this pink solution again when you put the boiling tube in cold water. And the reason for that is because the equilibrium is going to shift depending on that temperature change. And so we're moving the position of equilibrium using temperature there. Explain the observations and predict whether the formation of the blue colour is an exothermic or an endothermic process. So the formation of the blue colour is the left to right direction. That's what we're focusing on here. Well, I would say that at lower temperatures, the position of equilibrium shifts to the left. And whenever you move to a lower temperature with an equilibrium, you're going to shift in the exothermic direction. Likewise, vice versa. If you ever move an equilibrium to a higher temperature situation, you're always going to move in the endothermic direction. So the fact that this equilibrium shifted left when you placed it in the colder situation, that means to the left is the exothermic direction. So our to the right, which is what the question is asking about, is the endothermic direction. Moving on to question 3. This question is about ethane dioic acid and ethane dioate ions. The ethane dioate ion shown below can act as a bidentate ligand. And what I've done for you here is just added on the lone pairs that would be used to form those 2 coordinate bonds to the transition element ion. Ion 3 forms a complex ion with 3 ethane dioate ligands. Sorry, ethane dioate ions. They are bidentate ligands. My temptation there, just to use that. The complex ion has 2 optical isomers. Draw the 3D shapes of the optical isomers. And in your diagrams, loads of structure information here. In your diagram, show the structure of the ethane dioate ligands. All right, so a minute ago you were calling them ions, but good for you. And any overall charge. Now, the overall charge means what we put outside the square bracket. So just be vigilant for all these separate instructions and all the more reinforcement here. When it comes to the unified paper, read the full question. So here, in order to demonstrate the 3D shapes of the optical isomers, you really should demonstrate this mirror line down the middle and make sure that you've got your complex ions drawn on either side here, square brackets, all of that information needs to be mentioned here because they've told you to include the overall charge. And I've got my octahedral shape drawn around the middle like this. I've got the skeletal formula of the ligand shown around the outside. I've got my full structure here drawn nice and clearly. In order to get 3 marks, you've got to have all of this. So make it as clear as you can. The only other thing you could do to make this even more clear would be to label up the mirror line down the middle. Ethane dioic acid is present in rhubarb leaves. A student carries out a redox titration using aqueous cerium 4 sulfate to determine the percentage by mass of ethane dioic acid in rhubarb leaves. Spoiler alert, it's not a lot. Still quite dangerous. I think there's a recommendation that you shouldn't go around picking rhubarb leaves, for example. You shouldn't touch them, but it's not going to be a great percentage. In the titration, cerium 4 plus ions, oxidize ethane dioic acid in hot acid conditions. The cerium 4 plus ions have a yellow colour, and the cerium 3 plus, which are in the products just here, are colourless. Full description here of how they make up the solution in a 250 volumetric flask, and then 25 centimeters cubed of this solution, which contains the ethane dioic acid, is used in the titration, so that's it down here. And you've got then the cerium 4 plus is added from the burette. I want you to try and visualize this in the exam. Even maybe sketch out what I do here. This is exactly what I would do if I was given this question, or label up the equation with burette and conical flask like I've done here. That might make it even easier for you. They want to know at the start of this question what the color change is. What's the color change for the end point? Right, well, let's read the question again just a little bit more carefully. The cerium 4 plus is yellow, and it's in the burette. So picture it. You've got the burette in front of you. It's yellow. Big striking yellow color, like highlighter yellow. Picture it that way. And then in the conical flask below, you've got a colorless solution containing the ethane dioic acid. Now, every time you add a drop from the burette into the conical flask, that yellow solution is going to change color to colorless because we've been told it forms cerium 3 plus, which is colorless. All right? So it's going to land in here. A drop is going to land down in the conical flask and go colorless. Now, eventually, you're going to add a drop of cerium 4 plus from this burette that's going to land in the solution of the ethane dioic acid, and there's going to be no ethane dioic acid in there. And that drop is going to land in, that yellow drop is going to land in here. It's not going to react with anything, and the solution in the conical flask will therefore become yellow. So the unreacted cerium 4 plus will land in the conical flask eventually and not react, and cause the solution in that conical flask to be yellow. So the color change is colorless to yellow, as described here. Remember where you're looking in a titration practical. You're looking at that conical flask. Next up, we need to calculate the percentage by mass of ethane dioic acid in the rhubarb leaves. You need to give your answer to an appropriate number of significant figures. I really like this. Appropriate number, well, it's not that I really like it, it's just I think it's a clever way to test your precision of your answer in the exam. What we need to use is the minimum number of significant figures demonstrated by the question, which is 3. So we need to make sure that we give everything here to 3 significant figures. All right? So, titration results, the trial titer has been omitted for this. So we're not worried about anything that's been used as a rough titration or a trial titration, however you describe it at your college. Here we've got 3 sets of data, but we can only use results which are concordant, which are within 0.10 of each other. So the only titers I'm going to use in the average titer when it comes to the calculation just here are going to be 1 and 3. I'm not going to use the results of number 2. Only use those that are within 0.10 of each other. So in my calculation just here, I'm effectively going backwards through the stages. And even though this is a redox titration, we're following the same rules that come with a regular titration. We're going to figure out what the average titer is. We're then going to figure out the number of moles in that titer of whatever solution it is. And the solution is actually of the cerium 4 plus. So I'm going to use the concentration of the cerium 4 plus solution, the volume of the average titer, over 1,000 of course, and it tells me the number of moles per titer of the solution from the burette. Now, according to the reaction equation, the ratio is 2 to 1. And so since I'm going back towards, if I look in my equation just here, since I'm going back towards this ethane dioic acid just here, I'm going from 2 to 1 through there, I'm going to copy that ratio. And what I'm going to do with my data is I'm going to divide the moles of the solution from the burette, the cerium 4 plus, by 2 to mimic that ratio in the reaction equation to give me a number of moles here. And that's the number of moles of ethane dioic acid in a 25 centimeter cubed sample of the solution from the big 250 flask. And it's 5.8 times 10 to the power of negative 4 mol. Now, that's a 25 centimeter cubed sample from a big 250 solution. So to scale up, remember that that is going to be 1/10 of the total number of moles that we actually had in that big solution. So what I do now is I times by 10, and that tells me the number of moles of the ethane dioic acid in the 250 centimeter cubed solution. Now, for the mass, now that I've got the number of moles of the ethane dioic acid in the 250 centimeter cubed solution, for the mass, I'm going to do moles times molar mass, which is going to be the moles of the 250 solution multiplied by the molar mass of ethane dioic acid, which is 90. And that tells me that I've got 0.522 grams in a 250 centimeter cubed solution. Now, for my percentage, therefore, now, percentage by mass, I'm going to take that mass value that I've just calculated of ethane dioic acid in the 250 centimeter cubed solution, which is equal to the amount of ethane dioic acid in the sample of the rhubarb leaves. I'm going to divide that by the total amount of the rhubarb leaves, 82.68 grams, times 100, and my answer is 0.631%, a very low percentage to 3 significant figures, mimicking that precision of the question. Moving on to question 4. This question is about 2 compounds used in medicine. We've got cisplatin, which is a complex of platinum which is used in cancer treatment. What's the oxidation number of platinum in cisplatin? Well, the whole cisplatin complex ion just here is actually neutral, which means that despite the fact I've got 2 Cl- ligands in there, and of course the 2 neutral ammonia ligands, there's no overall charge on that complex ion. And the reason for that is because the platinum is +2. And that's how we get away there with having a neutral complex ion, even though you've got 2 ligands in there of Cl-, 2 chloride ligands. This is a really weird question. Cisplatin is prepared in a ligand substitution reaction which takes place in multiple steps. The equation for the final step forming cisplatin is shown below, and you've got this unusual structure here, which is really similar to cisplatin, except if you look at the 2, you can see that the difference is that you've got 1 less chloride ligand on the final cisplatin and 1 more ammonia instead. And actually, this structure has got a negative charge overall because it's got that extra Cl-, that extra chloride in the structure. And what they want you to do in the box just here is outline the mechanism, so that's draw, for the formation of cisplatin from that complex ion with the extra chloride and the 1 less ammonia, and use curly arrows and lone pairs where appropriate. It's worth noting in the mark scheme, as you can see I've written in the red here, that dipoles were ignored for this. Now this is organic meets inorganic, isn't it? Here I've drawn it 3-dimensionally for square planar. And the reason I did that is because of how they've drawn the product just here. So I kind of used what they've already done in the question to influence what I wanted to do elsewhere. So I've just been a little bit careful with that. Don't worry that I've decided to do my activity down here and they've got the NH3 there. That doesn't matter because my 2 remaining Cls are in the correct position. But I want to make sure that I'm almost replicating what they've done. The mark scheme gives guidance that suggests they would allow you just to use straight line bonds for this just here, but I erred on the side of caution for this and just tried to mirror what they've already done because they've done it there for me, so I think there's a clue in there potentially what they would prefer. We know a lot about curly arrow mechanisms. We know that ammonia has got a lone pair, which means it could be behaving here as a nucleophile. And so what we need to demonstrate is how the lone pair is attacking here this platinum, and that we're losing this Cl, this chloride ligand here, with a curly arrow movement like so. It's very nucleophilic substitution, isn't it? That's exactly what we can see. If we saw this in an organic chemistry lesson, this would be nucleophilic substitution. And so have that in your mind's eye when you're picturing this. It's a bit of a reach in terms of the combination of organic and inorganic, in terms of how you content the spec for this, what specification content you cover. But I like the crossover, actually. It really keeps you on your toes, I think, for this. Next bit, paracetamol is a solid organic compound used in tablets as a painkiller. Name the functional groups present in paracetamol. And so what I've done for you here is I've circled up what the functional groups are. I've given loose circlings to this. I know that in biology exams, for example, you're very often asked to put a box around a certain functional group and things. That doesn't really happen in chemistry exams. But I've got my phenol functional group here. I think some people imagine that phenol is when you have an OH on an aromatic ring and nothing else, but actually it's whenever you've got an OH directly connected to one of the carbons in the aromatic ring. So I've got a phenol functional group, and then I've technically got a secondary amide over here, but the mark scheme said to ignore any reference to classification of the amide and just accept amide. So ignore doesn't mean incorrect, by the way. It just meant that if you accidentally put primary amide here, they're likely to have ignored that, for instance. So I've written amide and phenol for this, and I thought this was really generous. 1 mark for each. Next up, a chemist prepares a pure solid sample of paracetamol from 4-nitrophenol in 2 stages. With a lot of these organic syntheses, we often have this big 1-to-1 ratio with the starting point and the final product, and that's really useful when it comes to the bigger calculations. Describe a two-stage synthesis of 5 grams of pure paracetamol from 4-nitrophenol. The overall percentage yield of paracetamol from 4-nitrophenol is 40%. So that 5 grams that we want to achieve, we've got to bear in mind that whatever mass of the 4-nitrophenol we're starting from, whatever moles we start from as a result of that mass, you're only going to be able to convert 40% of that into the paracetamol over here. We've got to bear that in mind when we go backwards through this. We've got to assume and account for a 60% loss. In your answer, include the mass of 4-nitrophenol required. So as I was just describing, we've got to take into account that 40%. The reagents and intermediate and details of the purification of paracetamol. So it's an organic solid. So we're talking about purification of organic solid, which is recrystallization. Now, you'll notice looking at my answer already, I've got subheaded sections, and the reason I've done that is because this is a level of response question. Subheadings, layout, quality of written communication, logical and well-structured reasoning, it's all got to be there. You've got to make sure that this answer is the most pristine thing you've ever done. Be self-aware. If you're a messy person, subheading, make it clear. Don't put bullet points near molecules. It'll look like free radicals, but I would make sure everything is nice and organized for this. So for this, I'm going to do my calculation. There are a couple of ways to do this. If you want to see an alternative way of doing it, dig through the mark scheme for this. It did give you some alternatives, but this for me was the most obvious way to go through the calculation. I figured out the moles of paracetamol that I need to achieve in 5 grams. So 5 grams of paracetamol gives me 0.0331 mole. Therefore, considering the 40% conversion, so I divided by 40 and times 100, I need 0.0828 mole of the 4-nitrophenol to get that many moles of paracetamol. Even though they're in a 1-to-1 ratio in the reaction equation, they're not a 1-to-1 ratio here, are they? And that's because of that 40% conversion. Therefore, the mass of the 4-nitrophenol I need is going to be this scaled up mole value multiplied by the molar mass of the 4-nitrophenol to give me 11.5 grams. Now, the reagents, I need to use tin and concentrated HCl according to the Module 6 specification. And my intermediate is going to be this structure here, which is 4-aminophenol. If in doubt, draw them out. That's the mantra I'd like to give you for this. Purification. Purification is a recrystallization. These are your common stages. They didn't say you had to hit all of this scientific information. It's level of response. They just want a majority of it. And the ones I've put in bullet points would be the ones I would teach for this. But the one in brackets here was also accepted. I've only ever seen this once in their mark schemes. I might need to have another look to see if they've accepted it in other years, but I've only ever seen this once. And I think it's here in this question because this is a level of response and they're a little bit more flexible. So here is, I'm not saying what I've put in the brackets you wouldn't do. I'm just saying I've not seen it in the mark schemes as often. So purification, dissolve the impure solid in the minimum amount of hot solvent, absolutely crucial. You would cool the solution in an ice bath, of course you would. Then, if you were in a practical and you weren't getting crystals, what you would do is scratch the inside of the vessel containing your solution that you're cooling down with a glass rod. Once you've then got a recrystallized pure solid, you would filter the solid under reduced pressure. You would wash the solid, and this would be on the filter paper in the Buchner funnel, with a small amount of cold solvent, and you would dry the solid as well. So that could be in an oven or air dry it or leave it to dry over the course of a week, perhaps in a fume hood. What's notable here is, if you're looking for a bit of an extension to this, they have asked you in a previous year to draw the apparatus, draw and label it, for this filtration under reduced pressure using the Buchner funnel and the Buchner flask. So maybe have a go at drawing that if you want to take this answer one step further. Moving on to question 5, a student carries out 2 experiments in the lab based on succinic acid, which is butane dioic acid. This is really cruel, I think. They've not shown the full structure. It's 4 carbons with a carboxylic acid group at either end. And I think all the way through here, they know what they're doing with this. They're making it difficult to interpret the molecules. If you were nervous in the exam, draw them out. If in doubt, draw them out. Go all the way through, draw them out. Have a look at what you think it looks like. Make it nice and clear for you. Aqueous succinic acid can be neutralized by aqueous sodium hydroxide. This reaction can be used to determine a value for the enthalpy change of neutralization. And we've got loads of details about a calorimeter practical here. Calculate a value for the enthalpy change of neutralization in kilojoules per mole. Assume that the density of all solutions and the specific heat capacity of the reaction mixture are the same as for water. So what that's telling you is that you can use the total volume of the reaction solution as the mass of the solution in Q equals mc delta T. All right? So it's a fairly straightforward calorimeter calculation here. Q equals mc delta T over 1,000. We're using 100 because that's the total volume of the solution. So 100 centimeters cubed is 100 grams. 4.18, show on the data sheet, specific heat capacity of water. 5 is the delta T. Gives me a value here in kilojoules of 2.09. I always do the divide by 1,000 just to save me a job later. Then the enthalpy change of reaction is actually going to be here, if I got the moles here, and notice please, I'm using the moles of succinic acid because I'm told that the sodium hydroxide is in excess. So I'm not going to use the moles of sodium hydroxide because they don't all react. So here I'm using the amount of the limiting reagent. And so my enthalpy change of the reaction is actually coming out as negative 105 kilojoules per mole just here. But that's not quite the enthalpy of neutralization because that's going to be per mole of water being formed, and at the moment this reaction equation value has got 2 H2O associated to it. So what I need to do here is divide this value by 2, and that gets me my enthalpy of neutralization quantity of negative 52.3 kilojoules per mole. Moving on to part B. Succinic acid is esterified by ethanol in the presence of an acid catalyst to form an equilibrium mixture. The equilibrium constant for this equilibrium can be calculated using the amounts in moles instead of concentrations of the components in the equilibrium mixture using expression 5.1. And just a little label for you, we've got products on the numerator and we've got reactants on the denominator here. As you always would, I'm just adding that label on because they ask you to write the reaction equation out in a moment. They give you a bit of a description of how they set up the equilibrium, and then they ask which technique could be used to determine the equilibrium amount of succinic acid. I do get people suggesting sometimes that you could use things like an oxidation and things like that. We're looking for amount here. We're looking for something that quantifies components of a mixture. And we've been told that it's an acid. You know it's going to be a titration. Then I'm told to write out the reaction equation for the equilibrium taking place. That's why I labelled up here products and reactants, because that's exactly what I need to write out here. My products on the correct side and my reactants on the correct side as well. So that awareness of the Kc expression is useful here. This bit's tricky, and I've given some extra labels to this to help you out. Draw the skeletal formula, had to be skeletal, of the ester present in the equilibrium mixture. So that's this bad boy over here. So each half of the molecule, because notice it's got a 2 here, so this bit here inside the brackets is just one half of the structure, contains 4 carbon atoms. So it's 8 carbon atoms in total. So I'm going through here, counting at 1, 2, 3, 4, 5, 6, 7, 8, all the way through there, like so. And you've got to be really careful how you draw this bit in the middle. I found when I've given this question to students before that people make a bit of a mistake with that connection, maybe leaving 1 carbon out perhaps. Take your time with this, visualize what it's meant to be. Kc is an equilibrium constant in terms of equilibrium concentrations, not moles. So why can the expression that uses moles at the top of this page be used as the Kc? And it's because the volume terms will cancel. Because if I was to figure out the units of Kc for this, I would have no units. And whenever you've got no units, that means your volume terms are cancelling out. And so actually, you could just use the moles at equilibrium of everything. I'm then asked here to calculate the value of Kc based on that information, and I need to show my working for this. Watch out for those dangerous show your working instructions, because if you just skip to the final answer, you may not get all the marks. Here what I've done is a quick sketch of the reaction equation again, and I've done a before and after when it comes to figuring out those equilibrium concentrations. I know the change for the acid over here. I'm told by the question, if I just go back up, that 0.05 mol of succinic acid was used to prepare the equilibrium. An analysis of the equilibrium using a titration, I'm assuming here from this answer, found that there was 0.02 mol of succinic acid present in the equilibrium mixture. So I know the change for the succinic acid is that it goes down by 0.03. Since it's in the same ratio with the ester over here, I know the ester goes up by 0.03, and that actually takes it to 0.03 because it started at 0. The water is in a 1:2 ratio, and so that means that the water is going to go up by twice as much as the acid went down by. so it goes up by 0.06. And the ethanol is going to go down by twice the amount that the acid went down by, because it's in a 1:2 ratio, and so it goes down by 0.06, and that takes it to 0.09. If you'd like to know more about calculating moles at equilibrium, there's a separate link to that tutorial in the video description, and I'll make sure it's in the cards at the top of the screen as well. So here are all my at equilibrium mole values that I didn't already have by the question. I was told the one for the succinic acid. I put them straight in. I've nearly forgotten to square here, so I'm just going to add that in actually. But I do need to square that ethanol value, so I do need to make sure that I've got a little square just there like that on that number. I would hate to get that wrong. And that's going to give me the final answer here of 0.667. There we are. Moving on to question 6. This question is about organic reactions. This is a real toughie. Compound A is formed when ethanol is mixed with OH- ions. So that's the alkali ion, effectively. So hydroxide ions here, which act as a catalyst. That's so incredibly important because you know that that means they're going to get regenerated. And we're going to need to know that information further down the page. The balanced equation is shown below. So here it is. This is the overall reaction equation. Notice the hydroxide ion isn't shown because we don't show the catalyst in the overall equation. We might write it on the arrow occasionally, but we don't show it in the overall reaction equation. Give the systematic name of compound A. It's 3-hydroxybutanol. What's the reaction taking place? It's an addition. So it's an addition because I've only got one product over here. Like electrophilic addition. So if you had an alkene and HBr, it's an addition reaction. Two things being added together to make one product. This is the bit that I think is really complicated. And I shouldn't laugh over it, but I do think it's a really tricky question. There's lots of moving parts to this, and there was a lot of variety when it came to the mark scheme as well. Reaction 6.1 takes place in 2 steps. The hydroxide ions act as a catalyst in step 1. Ethanol reacts with the OH- ions to set up an acid-base equilibrium. And in step 2, compound A is formed, and that's all the guidance you get. It's really vague. I think it's really tricky. First bullet point here says, complete the equilibrium for step 1 and label the conjugate acid-base pairs as A1, B1, A2, and B2. Now remember, 1 and 1 is a pair, 2 and 2 is a pair. So a pair needs an acid and a base, all right? So there's a pair, there's a pair, all right? And the pairs should look like twins, but one of them is wearing a hat. The acid is wearing the hat. The acid has got the extra H+. The only difference between them should be the loss or gain of that proton, all right? Again, I've got another tutorial video if you want it about acid-base pairs. So here for this, you've got to decide. Obviously, the hydroxide ion is going to be the it's going to be the proton acceptor here. So I've got to lose the hydrogen from this aldehyde structure here. My instinct here was to lose the hydrogen from the functional group of the aldehyde. I wouldn't try and lose the H+ from the CH3 group. That doesn't typically happen. So I've decided to lose it from here, although they did accept you taking it away from the CH3 group in the mark scheme. I have seen them be quite mean before, though, when it comes to acid group versions of this. So just exercise a bit of caution, but have a look at the mark scheme if you think your version of the answer could be accepted. Here, if you notice, the difference between these two structures for me is quite literally that one is wearing a hat. So this structure over here has got an extra H+ compared to this one, making this the acid and this the base in the pair. Now, I've labeled them as A2 and B2. I could have labeled them as A1 and B1. That would have been fine. The mark scheme allowed for that. You can interchange the numbers here. I've then got, for the other, notice it's twins, but one is wearing a hat. So the H2O has got its hat on, whereas the OH- is hatless. And so they're going to be the 1 and 1 or the 2 and 2. And the OH- is going to be the base, and the H2O is going to be the acid. Then for step 2, there's a lot going on here to get 3 marks for this. It's really heavy. The whole thing involves 3 marks. I really think this final part is really heavy going. Suggest the equation for step 2. Right. You've got to make sure in this that you make the product. You've got to make sure you make compound A. You've also got to kick back out the OH- because it's got to be regenerated because it's the catalyst, and we put it in step 1. And you've got to use your intermediate from here, whatever structure it is. You can either list it out as the structure or you can draw it like I've done. And if that wasn't difficult enough, you've got to use the other aldehyde molecule that you haven't even come across yet, which is this one, This is a lot of effort for this reaction equation. I think it's really hard work, but all those moving parts need to be considered. So I'll just repeat them. We need to make sure we cancel out the OH minus. We need to make sure we make compound A, and we also need to make sure that we use our intermediate and the other aldehyde from the overall equation. What a lot to consider. Really difficult question. So well done if you've done this and got that right. But that's unified chemistry. It's going to be difficult. A similar reaction takes place when propanone is mixed with OH minus ions. Draw the structure of the organic product of this reaction. If we have a look up here, instead of ethanol, we're now being suggested that we're using propanone. All right. Now, all the way up here, notice we've used ethanol and we've created this structure here for compound A. So 2 carbons in each of the starting materials gave me 4 carbons overall. So if I swap out these aldehydes for ketones, the only bit that changes is these H's just here. They become CH3s. And so down here, what I've done is to try and make this as visible as possible for you. I've redrawn compound A, but I've changed these CH3 groups here. So what I had was these H's, they are now CH3s down here, okay? So if I don't use ethanol, instead I use the ketone propanone, then I end up with these CH3 groups where those H's were to begin with. So hopefully that makes that nice and visual for you. Moving on to the final part of the paper, and this is a great revision question. Many organic reactions use electrophiles as reagents. Explain the role of electrophiles in organic chemistry. Pour your heart out. It's a level of response. Keep it subheaded. Keep it clear. I know it's a pain that you have to draw mechanisms over line space, but deal with it, yeah? Pour your heart out with this question. Your answer should include 1 reaction of an aliphatic compound and 1 reaction of an aromatic compound. You could do a version of this, not quite aromatic necessarily, but you could do a version of this with a nucleophile. So you've got nucleophilic addition and nucleophilic substitution on your A level. I would have a think about how you could do a similar kind of question, testing yourself on all of that. So, electrophiles are electron pair acceptors. That's the first thing I'm going to mention about this. And then I'm giving my 2 examples, one from Module 4, which is electrophilic addition, and one from Module 6, which is the electrophilic substitution, of how I know electrophiles behave. And I've got my curly arrow mechanisms drawn out in full, loads of correct positioning with the curly arrow, so this is really important. And don't forget the overall reaction equations as well, please. Even I myself very nearly left them out. When it comes to when it comes to the electrophilic substitution, I would also make sure you notice that in the mark scheme, in the extra detail, they did put emphasis on you including the formation of the electrophile for this one, because there are these separate equations, and regenerating the catalyst. So you've got that extra information in Module 6 associated to electrophilic substitution. All of them include the version of this. I went for nitration of benzene. Here, there was no prescriptive what you had to go with. It's just my instinct is, when it comes to electrophilic addition, I'm going to use the bromine water one. I know that bromine water gets decolorized in electrophilic addition, so I just tend to use it, and it's just easier. Could I used HBr? Could I have used an unsymmetrical alkene and got major minor products? Yeah, and the mark scheme did say that you could include that. I'm just creating work for myself there, though, and I'm getting my point across here just using Br2. For electrophilic substitution, I've kept it to the nitration because I know I'm going to get it absolutely 100% right for this. I've given as much detail as I can. I've regenerated the catalyst of the H2SO4. I've got the full outline of the mechanism down here as well. I've got all of the correct intermediate, the curly arrow positioning. I've not forgotten the H+. This is an all guns blazing answer. You've got to really show them line by line, make it clear what you're doing. And again, you've got to demonstrate that your answer follows a clear, well-structured, organized, logical line of reasoning. It's got to be absolutely pristine. So when it comes to level of response, don't skimp on the detail and keep that organization high. Thank you so much for watching this very long tutorial, which covers the Unified Chemistry paper from 2018 on the OCR specification. If you did find the video helpful, I would really, really appreciate it, please, if you could give this video a like before you go, and consider subscribing to my channel to stay updated ahead of your chemistry exams. And until next time, everybody, happy revising.